high frequency, low frequency, ultra high frequency behavior of transistor amplifier circuits. Remember that? It's still hell on earth when I remember that. I had that course in 1982. I still have nightmares about that class. Anyways, you did something called frequency response and Bode plots, and it's transfer function. You know, where you have this circuit model, and then you say, okay, I'm going to apply a voltage here, Vn, I measure V out. I do it at 1 hertz. Then I do it at 2 hertz. Then I do it at 3 hertz. And I come up with something called a transfer function. And the transfer function is basically V out divided by Vn equals 20 times the common, oh wait, the transfer function is 20 times the common log of V out divided by Vn. Y'all remember this, engineers? No? Yeah, no,
I don't remember it.
20 times the common log of V out over Vn, you're looking at reflection points, 3 dB drop, and all this sort of stuff. And so what it is like you come up with a circuit, and say this is the equivalent circuit of a transformer. It's not. I'm just drawing a bunch of R, L's, and C's, okay? But let's pretend this is the equivalent circuit, okay? It looks something like this. The main thing is that it's a combination of resistors, capacitors, and inductors. Capacitors and inductors, under AC conditions, behave like resistors. You can model them as resistors. And their resistance or reactance is a function of the frequency. So anyways, you have these things, you apply a voltage here, okay? You apply a voltage here, Vn, and then you measure the voltage that comes out, V out. To quote Jethro Bodine, gazatas over the gazintas, you know? You do the out over in, divide it, you take the log, you multiply it by 10. Out is going to be less than in, so this number is going to be less than 1, so you're going to have and the log of a number less than 1 is a negative number, so you're going to have negative numbers. And that's called the gain, or that's the that's the value you get. And then you plot it. You plot it as a function of frequency. And let's say we start off here, and in the case of the SFRA, sweep frequency response analysis, you start out at 10 hertz and you go out to 2 million hertz. You're sweeping the frequency. So you do it at 10 hertz, you get a number, you make a calculation, you plot it. Okay? You then go to 11 hertz, and you go, or 12 hertz, or 100 hertz, or whatever, and you go all the way up to 2 million. And you get, in the case of this, you get what's called a transfer function. And it might look something like this. And when the transformer is new, when the transformer is healthy, and if you take the transformer, I love some of these terms, fully filled and dressed. So filled with oil, all the bushings on it, as we say in Boston, the radiators on it, everything, control cabinet, everything. I'm sorry? Conservator.
Heck with it, let's go to the bar.
Let's go to the bar. Yeah. but you know, so you put everything in, because this is very dependent upon geometry. You know, the size of the bushings you use. You know, and if you replace the bushings, you had trench bushings which had a C1 of them to say number 300, and then you put in ABBO plus C's and it was a C1 of 450 or 500, you're going to get a different response up here. But this is almost like what they call signature analysis too. That a healthy unit is going to look like this. And if there's been a change of some sort, a physical change, it's going to look different. It might look different here, it might look different here, it might look different here. But what we are looking for here is, and it's like what we talked about with capacitance, and if you ever look at leakage reactance and whatever, is a physical change. More and more utilities, almost every utility now has this in their spec that the transformer manufacturer does in SFRA, the factory